So it's 7:01. So let's start our session. Yeah, good evening, everyone. So today we are on the fourth day of our workshop, and today we have an industry expert with us, Mr. Vijay Nair. Let me give a brief intro about him. So currently he is with Levi Strauss and Co. as regional head of data analytics and AI for the Asia Pacific, Middle East, and Africa regions. He is a data driven and people centric global leader with proven expertise in building analytics and data capability, managing large teams, and handling multiple stakeholder relationships. He is also a part of the leadership team at Lowe's India, the Bangalore based GIC for the Fortune 50. He has ranked one among the top 50 analytics data science leaders in the country as recognized by the Analytics India magazine. He is also the winner of several industry awards, including Predictive Model and Best Analytics Team. And he is having more than 3+ years of experience with international exposure as part of the operational strategy team for the world's largest online grocery retailer. And when we come to his educational background, he did his MBA from IIM Calcutta and his BTech from BITS Pilani in the Department of Electronics and Electrical Engineering. And he's a speaker at various analytics forums, including the Analytics Leader Summit at Indonesia, Cypher, which is India's largest analytics conference, Machine Conference in Mumbai, and top business schools like ISB and IIMs. He's also a guest faculty for the AI and ML program offered by Great Learning and University of Texas. Okay, we welcome you, sir. Over to you now.
Thank you, Dr. Srija. Excited to be here and talking to you folks. After that detailed introduction, very kind introduction by Dr. Srija, what I wanted to say was, we have three topics to cover today. But the value I think I can add coming into this is really talking about the industry perspective to these topics. A lot of these topics, I'm sure you must have covered it in some way, shape, or form as part of your education. But what I thought I would do is to spend some time talking about the theory, talking about a practical example on Python, and then also talking about some of the industry applications in terms of why this is useful and why some of this is so very relevant to some of the use cases that we're doing in the industry. Okay. With that, what I'm going to do is I'm going to share my screen. So if one of you could confirm, please, Dr. Srija, if you could confirm if you can see my screen.
Yes, it's visible.
All right, perfect. So what I'm going to do is we'll start off, covering a little bit of the theory. So we have three topics to kind of cover today, which is relational analysis between variables. We'll talk about things like correlation and why correlation is so useful from the perspective of data science, and then get into regression, which is one of the most used algorithms in the industry. And in the final half an hour, I'll show you a case study on Python in terms of how you can apply some of the concepts that we've learned or refreshed as part of this curriculum, right? So the first thing that I'll do is start with the basics. So I'm going to look at the bigger screen over here at the moment that I have. So if you look at data, and I'm taking you back a couple of sessions earlier, data can be broadly split into what I would call as categorical data and numerical data, right? Some people call it qualitative and quantitative. I just like to call it categorical and numerical. Most data can kind of be split like that, right? Now, if you remember the session from before, categorical can be further split into what we call nominal data, and the other bit is ordinal data. So can someone tell me from their memory, what is the difference between nominal and ordinal? And sorry, I might not have access to chat because I'll have to keep switching screens, but if you could unmute and say, that would be great too. Anyone know the difference between nominal and ordinal data? Okay, I'm not sure how to access chat while I'm presenting, but let me see if there's any results. Okay, so let me give you the answer. So nominal, yeah.
Ordinal is in some sequence.
Perfect. All right. So ordinal, very simply, and I like to use as little math and terminology as possible. So ordinal very simply means ranking matters, right? So the ranking matters. So what do I mean by that? Again, let's take a simple example. So I work for Levi's. Levi's is an apparel company, and we're always thinking all the time in terms of what size garments to produce, right? So when we are talking about t-shirts, we are talking about sizes like small, medium, and large. Now, why is it ordinal data? Because it has a ranking. So small is less than medium, medium is less than large. If you think of waist sizes for jeans, you have 30, 32, 34. And obviously there's a ranking. So 30 is less than 32, 32 is less than 34, right? So any data like this, which is categorical and which has ranking, is basically called ordinal data. And categorical data, which doesn't have ranking, obviously, is called nominal data. And a good example of nominal data is gender related data, right? So if you look at gender, which is male, female, really there's no ranking for male, female. If the answer to a question is yes and a no, really there's no ranking for a yes and a no. If you're looking at describing cars and what cars are on the road, you might have cars like Maruti, Hyundai, Audi, BMW, etc. There's really no ranking to it, right? So this kind of data is what we call nominal data. All right. Now, on the other hand, if we now shift to numerical data is kind of split into two categories. So you've got, first of all, discrete data. All right. Anyone knows the definition of discrete? If you could please unmute and tell me, what is discrete data?
Uh, exact value with some interval for
Yeah,
that.
yeah. So very simply put
It's not
again,
continuous, rather, I mean to say.
The data
perfect.
is not continuous.
Exactly. So, in other words, data that can be counted, right? So, for example, if you look at a car park, the number of cars in a car park is something that can be counted, and therefore it's called discrete data. Number of students in a class can be counted, and therefore it's called discrete data. Number of rooms in a house can be counted, and that's called discrete data as well, right? So, anything that can be counted is called discrete data. On the other hand, anything that can't be counted is called continuous data, right? So good examples of that is, temperature, right? Because you could describe temperature as 34.234, whatever. So temperature, of course, can be measured, but if you think about, the limitations of measurement, if you pick up a thermometer and actually measure the temperature, it might say 34.3 or 34.35, but in reality, the temperature is probably 34.35678 9, whatever, right? So it's got a lot of decimal places to it. So it really can't be counted. Another
Just
good
one question here.
sure.
Yeah, so about the temperature, right? So temperature, I think it should be ordinal because when we say 30 degree and 31 degree, right? So when we talk about numerical data, right, we have some mathematics to do, right? Addition and subtraction we can do, multiplication we can do, right? But in temperature, difference between 41 degree and 42 degree is different from 29 degree and 30 degree, or minus 1 degree to 0 degree.
Yes, but it's not categorical data, correct? It is continuous, right? So for
Yeah,
example, you have 40 point,
it should not be considered as numerical here.
it shouldn't be considered.
As
Uh,
numerical when we are considering about the analytics.
so for example, if you take another example like weight, for example, right? Would you
Yeah.
consider weight as categorical?
Uh,
Would you consider height as categorical?
no.
No, right? Yes, 30 kgs is more than 31 kgs and 32 is more than 31. But the point over here is this is continuous data, right? Which
Yeah.
really can't be counted. And that's the whole idea of continuous numerical data that we're talking about, right?
Yeah.
Okay. So all of this is really sort of continuous data in a way, all right? Now, for our purposes, and there's a reason I was kind of talking about this completely for our purposes, when we talk about relationship between data, relationship between variables, just for our purposes, let's call this quantitative data. So I'll call it Q, right? I'll just represent it with Q. And then categorical, I'll represent it with C. All right. And there's a reason I'm doing that. But I just wanted to start off giving the introduction in terms of what is numerical data versus categorical data. Let me just call it Q and C in terms of quantitative data and qualitative data. Okay. So that is one part of it. All right. So the second thing, before we jump into sort of the relational analysis, and I'm going to take this off, is so I'm going to write this over here so that we kind of remember it. So in terms of data types, you have quantitative and you have categorical, right? And the second thing that we need to talk about when we talk about data and sort of relationships between data and stuff like that is, how do you describe data, right? And again, I'm not being very mathematical about it. I'm being more application driven from that perspective. If you think about describing data and if you think about it very broadly, there's two ways you can describe data. There's one which is you can describe it in a visual or a graphical way, right? And the second is that you can use numbers to describe your data, right? Quantitative measures to describe your data, all right? So what do I really mean by that? So if you look at, for example, visual and graphical analysis of data, you can describe data using shape of the data, right? So for example, if you look at weight of students in a class, it's probably, I mean, if you look at enough data, it's probably, a bell-shaped curve. If you look at people's wealth, it's probably data that is skewed towards one side, depending on the country that you're talking about, etc. Right? So you can describe it using shape of data, right? So that's visually that you can look at the data. The other thing that you can describe when you look at the visual side of things is the spread of the data. And why is the spread of data important? When you're using the data, let's say, for example, to make predictions, data that is very, very spread or has a very high standard deviation behaves very differently from data that doesn't have too much standard deviation. And therefore, it's easy to make predictions about data that doesn't move a lot as compared to data that moves a lot, right? Then you can also use the visual representation of data to understand, for example, whether they are outliers in the data and so on and so forth, right? But my point being over here, when you're describing data, there's either visually you can describe data or from a number perspective. And when I mean from a number perspective, there's things like, you've learned this in the previous sessions, you could describe it using mean, which describes sort of the center of the data. You can use things like standard deviation, which kind of describes the spread of the data. You can describe skew mathematically and so on and so forth. Now the analogy, so you might be wondering, why are we talking about describing data from a visual perspective and a number perspective? And I'll give the whole idea of when we look at it from a data science perspective and we are trying to solve problems. The best way to understand this is if you go to a doctor and let's say, for example, you go with symptoms of a fever or you go with symptoms of a disease, there are two ways in which a good doctor would analyze your condition or would diagnose your disease, right? So they would look at you visually and say, okay, you seem to look tired, you seem to look weak, you seem to have fever, and so on and so forth. But at the same time, a great doctor would also look at the numbers. They'd probably ask you to get a blood test and so on and so forth, and then come up with a diagnosis for what your disease is. So very similarly, when we are describing data, understanding data for the purposes of analysis, it's important to do both the visual side of things as well as the numerical side of things in terms of understanding the data, all right? So what I'll do over here is to say data is quantitative and categorical, right? And then how you describe data is either using numbers or using, graphical or visual data, right? So these are the two things, just as a start to understand how do we understand relationships between different data. Okay. So any questions on this? Or should I keep moving? All right. So I'm going to take this off. Right, and get into the third section, which is really the crux of what we are trying to do, right? So now, if we talk about analyzing data, right? Analyzing data, and I'm sure you'd have heard of this before. there are three ways of analyzing data. So you've got what is called univariate analysis, you've got bivariate analysis, and you've got multivariate analysis, right? So can anyone tell me what is univariate analysis?
It's just
Single
a single.
variable.
Exactly. It's a single variable, right? It's a single variable. So you are understanding the distribution of a variable. You're understanding the mean, median, mode, or let's say, for example, the standard deviation of a variable. So you're just analyzing the variable according to yourself. Good example is, I like to take a lot of examples from the medical field. If you're doing, a predictive analysis, let's say, for example, on predicting cholesterol among the general population, cholesterol could be the variable that you're analyzing. And if you look at blood samples of individuals, you will probably notice cholesterol varies anywhere in between 100, which is great cholesterol control, to, let's say, for example, even 500 in people with very, very poor cholesterol control. And as some of you might know, 200 is the range beyond which doctors get really, really worried about, cholesterol, and they, advise you to have statins, and do lifestyle changes and stuff like that. So here we just analyzing one variable and the distribution of the variable, and this is called univariate. So if we were to visually analyze the data over here, we would use things like, for example, box plots, things like, for example, bar plots, etc., to look at the shape of the data. And we would use numerical measures like mean, median, mode, standard deviation to kind of describe the data from a numerical perspective, right? So this is stuff that you've done in the previous sessions, right? What we will be focusing on today is really a lot on bivariate and sometime then on multivariate analysis. Okay, so we'll talk about bivariate and multivariate analysis, but given the curriculum, most of our time we'll be spending on bivariate analysis in here and understanding that a little bit better. Okay, so I'm going to take this off. Sorry. And we will now focus on bivariate data. All right. So what's the idea of bivariate data? As the name suggests, bivariate means analyzing typically two variables, which is x and y. So two variables, x1, x2, xy, whatever, right? So two variables in here. And if you think about it, there are three combinations of data that we could typically look at. All right. So what are the three combinations? Both of these are quantitative data. So both of these are quantitative data. So both X and Y are quantitative data. You could have a case where either X is quantitative, Y is categorical, or X is categorical and Y is quantitative. Or you could have a third case, for example, where X is categorical and Y is categorical. All right. So these are the only three cases present in terms of data. And we look at how would you describe relationship between data if one of these three cases kind of occur. All right. So any questions up till this stage in terms of understanding why we've done what we've done and how we're describing data and stuff? Okay. All right. So the first thing that we'll do is understand how do we describe relationship between data from a visual perspective when we consider these three scenarios, right? So the first one we will consider is actually categorical, because, if you look at the data that we analyze from a data science perspective, a lot of this is QQ, which is why I'm kind of keeping it for the end. We'll start off with categorical, then go to QC, and then go to QQ in a way. So let's look at examples of where we have categorical data. Okay. So the example that I'll pick to describe the visual understanding of data is, in the simplest possible way, use a tabular format to kind of understand the relationship between categorical and categorical data. So let's take an example to understand this. If you're interested in how do males perform in an exam versus females, you could describe it using a very simple table where you have male, female, pass, and fail. All right. And then I'm going to put some Arbit numbers in here so that we can use this analogy here. So this is going to be 20, 50, 50, and let's say 100. So a simple table would help you analyze the relationship between these two variables, which is categorical and categorical, where you could say that the probability of a male, um, the probability of someone passing being a male as is 35 divided by 100, which is 0.35. The probability of females passing in this population is so on and so forth. So you can very quickly find out proportions, probabilities. So you could say among all males, what is the probability of passing? Among all females, what is the probability of passing? And so on and so forth, right? So you could do simple probability analysis to find out one, you know, the relationship between the two variables, and a lot of other things in terms of conclusions that you could come to with this very simple table. Now, if you think table is not really a visual form of looking at the data, what you could also do is what is called a stack box plot, sorry, stack bar plot, right? So what you could do is to have x-axis which describes male and female, y-axis which has, let's say, for example, pass percentages, right? So let's say, for example, it varies from 0 to 100, and you could split this essentially to something like this, right? So for example, you could say in males, about 20% of them failed, right? 20% of them failed and 80% of them passed, right? Whereas with females, only 10% of them failed and 90% of it passed. Now, why is this useful? Because you could very quickly say that females are far better at this exam versus males. You could also kind of look at, instead of percentages, you could look at absolute numbers to see from an absolute perspective how many more males are passed with respect to females, and so on and so forth, right? So these are two sort of classic representations from a visual perspective in terms of comparing categorical data to categorical data, right? So that's the first part of it. The second part of it is really, if you look at the second case, which is qualitative and categorical, right? So let's talk about some ways in which we can understand the relationship between qualitative data and categorical data. So again, I'll take a medical example, and we will look at, for example, one variable. So let's say, for example, one variable describes, so the quantitative variable is cholesterol, okay, the level of cholesterol, and the categorical variable is really the gender, all right? So you've got males and you've got females, right? And one way to understand, the relationship between a quant and a categorical variable is to, draw a box plot. Okay, so if I draw a box plot, so hopefully you know what a box plot is. So if I draw a box plot in here, all right, and this is the box plot for males, let's say, and let's say, for example, you have a box plot which is here for females. You could very quickly say that females in general tend to have a higher level of cholesterol as compared to males. Now, why is that the case? Obviously, this doesn't say that, but you could very quickly compare and say females have a higher cholesterol than males. You could very quickly say that the range of cholesterol for females varies from whatever this minimum value is to this maximum value. You could very quickly look at outliers in terms of cholesterol for males as well as females. So this becomes like a really good way of understanding the relationship between a quantitative variable, which in this case, for example, is cholesterol, and a qualitative variable, which is a categorical variable in this case, which is, let's say, the male, female, or the gender data here, right? So that's the other way of describing it. Right. Any questions so far in terms of quantitative categorical? And of course, there are many other ways to kind of show this data, but hopefully you're now getting a sense of how do we compare from a visual perspective different variables basis whether they are categorical or quant or whatever, right? Okay. But the most interesting thing, and where a lot of the data is from an industry perspective, is the third case where both data types are quantitative. All right. So let me take a classic example and talk about what happens if two data are quantitative. So the best way to kind of show this, or one of the really good ways to show this, is using what is called a scatter plot. Okay, using what is called a scatter plot. Now, what does a scatter plot do? A scatter plot helps compare, two quantitative variables. So let me take an example. If you're looking at the price of a house versus the square feet of the house, and you take different data points and you kind of plot that on a graph, you're going to get a scatter plot that looks like this, right? And each point over here essentially represents, at a certain square feet of house, what is the price of the house, right? At this certain square feet of house, what is the price of the house, and so on and so forth. So a scatter plot is a great way of representing the relationship between two quantitative variables, all right? And this is typically what you would expect if you did price versus square foot, all right? But if you're taking real life data, you might see data points coming over here and data points coming over here. So let me ask you at this stage, what is this, what is this telling you? Is this even possible? And is this even possible? Can someone describe to me why this would happen?
Both can be possible. Certain areas, there may not match the square feet and price.
Yeah. So can you tell me examples of where that might happen? Let's start with this, which is low
For
square feet and
example,
very high
suppose
price.
in particular area there is a dominance of one, uh, what I can say, one community, and if some other person will try to go there, then
Yeah, you could do that. Or if I keep it really simple, right? I don't know if any one of you is from Bombay, but if you look at Bombay, where people live in typical matchboxes, and sorry if any one of you is living in Bombay, I live in Bangalore. Bangalore's much bigger size of houses, etc. For very, very small square feet sizes, you have very, very high price, right? South Bombay, especially if you have a beach facing house, is probably the most expensive piece of real estate in the world. So this is where, although square feet is very low, the price per square feet, or the price of the house is really, really high, right? On the other hand, you might have rural areas where you have these massive farmhouses. The square feet could be massive, but the price is low just because they are very, very far away from, the city, right? So a scatter plot is a wonderful way of showing relationships between two quantitative variables, and it's extremely useful as you enter the world of machine learning to understand the relationships between various variables and stuff. All right. So this is visually just showing you how would you describe relationships between two variables. But I also wanted to spend time before we head to the quantitative measures and the numerical measures of how do you describe relationships between variables. I wanted to sort of ask you, how would you interpret data? And I'll kind of focus on quant versus quant for a moment. All right. So I'm going to take this off if there's no more questions. This. Okay. So what I'm going to do is sort of draw three plots. And if you've understood what I've been talking about so far, you should be able to easily give me examples of where you might see that from a real life perspective. Okay. So imagine I have three graphs, right? Imagine I have three graphs. So one graph is a scatter plot that looks like this, right? Where, as x increases, y increases. Another scatter plot which looks something like this. I'm really bad at drawing, but hopefully you get the gist of what I'm trying to do. And then you have a scatter plot that kind of looks like this. Okay. And then finally, a scatter plot which looks exactly the opposite, which is like this. Okay. All right. So what I'm going to ask you to do is think about examples in real life where this is the case, right? So the first one is easy. We talked about, price of the house versus square feet of the house could be one example. Can anyone give me another example of where you would see this kind of a scatter plot between two quantitative variables? Any other examples that come to life, come to mind? Anyone? Where you see if with increase in X, you see an increase in Y. Any examples from real life?
Maybe height versus weight. Normally, as height grows, the weight grows.
Height versus weight. Okay. Well, there could be many other examples, right? So, for
Yes.
example, if you could see age versus income, typically, as age increases, the income of individuals increase, and obviously there are exceptions. There's Dhirubhai Ambani's son or Mukesh Ambani's son or whatever might have less age and he'll have a higher income, and on the other side, you might have too much age and hardly any income left, right? So you have all those cases, but in general, with increase in age, you have an increase in income, right? And there are many other examples of that. Can anyone give me an example of this kind of a scatter plot and where you would find it in real life? So as X increases, Y decreases.
Age versus wealth. Not wealth. Sorry, age versus health.
Age
I don't
versus
know how.
health, lovely,
I don't know how to
lovely,
measure a health, but I guess as age increases, health decreases.
lovely. So if you were to describe health in form of some
Yeah.
numerical measure, health decreases. Great, great
Yeah.
example.
So how much amount we pay for health? Well-being.
that
Yeah.
that increases, right? As age
Yeah. Yeah.
increases, the amount of the money that you're paying for health, that perfectly fits over here. Yeah.
Yeah. Yeah. Yeah. Yeah.
Age versus energy, sir.
Age versus energy, yes, absolutely. So you mean physical energy? Of course, yes,
Yeah.
right?
Yes, sir.
So age, physical energy, if that can be measured or whatever. You could also say age versus appetite, and you can measure that in number of calories. And typically, as age increases, as you get older and older, if you get into older age, your calorie consumption, unless you are very extreme, goes down. People typically feel less hungry, apart from the fact that they have to contend with all sorts of diseases and stuff. So that could be another example in there, right? In a way, the classic example from an industry perspective. So I deal with a lot of this, working for a retailer, is price versus demand, right? As the price increases, the demand decreases. So this is a graph that we see day in and day out. I've worked in, grocery, I've worked in home and, home improvement and furnishings, and I now work in apparel. This graph is something that we see all the time, which is that as the price increases, the demand increases, right? On that note, can you tell me an industry where if the price increases, the demand also increases? Do you know of an example? The price increases and the demand increases.
Like gold share.
Gold, the price increases, demand increases, maybe, but there is a special class of industry where this actually happens. Anyone knows that?
Mobiles.
Mobiles, but iPhone is not iPhone is the most expensive phone, right? iPhone is not the is not the highest selling phone, especially in India and stuff like that. So I'll give you the answer. You think of luxury goods. Okay, so think of
Car.
retailers like Louis Vuitton, Gucci, Burberry. You think of luxury cars like BMW, Porsche, etc. As the price increases, the demand actually increases simply because people feel, there is a snob value attached to the good. All right. And therefore, we've seen many instances where I'll give you a good example, even from home furnishing chandeliers, right? People are very, very inelastic when it comes to price. You buy a chandelier because, you want to show off, or, it adds to the decorative appeal of the house. So actually, prices have nothing, they probably have very little demand, little to do with the demand. In fact, the more expensive you make the product, people think that, I can show it off even more, and therefore the demand keeps going. So luxury goods, actually, you see the opposite, right? Okay, so this is the scatter plot for, as x increases, y increases. Can someone tell me a good example from real life in terms of this particular scatter plot?
Rainfall versus months.
Rainfall versus months. Interesting. So you're saying, so month is over here. So month is typically a categorical variable, right? So month 1, 2, 3, 4, and all of that stuff. But it's a good attempt, actually. I'm looking for two, quantitative
Sunlight.
variables. Sorry, say that again.
No,
Here,
daylight, sir.
here we can say
Huh.
age versus health, because at certain age, initially health will get improved as you become going elder and elder, but after certain level it will get decreasing.
Correct, correct. But I think the graph for age versus health looks something like this, right? Because, up until 2025, you're pretty healthy. From 25 until 65, your health is going down continuously,
Sir,
right?
for the actors, demand versus age.
Great one, great one. Okay, so how much they are paid versus their age, it goes up until they hit a peak, and then yeah, you're absolutely right. Yeah, it's a good example. Yeah. Okay, the one that the
Time,
automobile. Sorry, somebody else had another one.
sir, time versus daylight, sir. Like
Time versus daylight.
morning
So
time.
noon, for
Mhm.
example, the amount of
Yeah.
sunlight is the maximum, and then it drops off. Perfect, great. Another one that the automobile industry typically sees is, speed versus mileage, right? And that's the case study that we'll be looking at today. As the speed increases, so if you're driving your car at a very low speed, your mileage tends to be very low until you hit roughly about 40 to 50 kilometers per hour. That's when it's the sweet spot when it comes to mileage. But then if you keep driving very fast, mileage drops, and that's one more reason why you don't want to be driving fast, apart from the fact that it can be dangerous. Okay, so great, this is great. What about this kind of a graph, which is ulta of this?
Sir, COVID-19.
COVID-19,
So
meaning?
what happened today is like we got almost reached to ground, and now
Yeah.
people are saying maybe in fourth wave we'll reach up.
Okay. Okay.
Yeah.
So yeah,
So uh, age and free time.
age and free time, great. So as age increases, free time decreases up to a point where your retirement, fantastic. Any other examples? Any other examples of this? They also say, I mean, again, just using a funny example, the amount of happiness in a relationship. So when you get married, your expectations are high, especially in a love marriage. You get married, your happiness is very high. Then after some time, it drops, and then you feel like, acha, it's okay, yeah, we've got to adjust and whatever. And then as age increases, the happiness goes up till you become an old couple and you can't live without each other, right? Anyway, there are multiple examples of this, and I'm happy that you've got the relationship right, and you've understood this. Now, this becomes really, really useful. All of this becomes really, really useful when we get into machine learning, and we kind of talk about predictions, because depending on the relationship, you can draw multiple sort of interpretations in terms of what you're seeing in the data and stuff like that, right? So this is the whole idea of, visually kind of describing data to see, what sense we can make out of it, right? So that's the visual side of the data. But then the other side of the data, like I said, as a doctor, you just don't see the patient. You also look at things like the temperature, blood parameters, etc. You also got to look at the numerical side of data in order to make the interpretations that you need to do, right? And what we will do is we will use one very powerful measure of data, which is called correlation, to understand what is the relationship between data. And what I'm going to do over here is I will keep this over here and I'll actually shift to a presentation to talk about, how do we describe data from a numerical perspective, which is the correlation side of things. All right. So let me very quickly open a presentation for correlation. So first of all, correlation is very simply, from a plain English perspective, used to describe the relationship between two variables, right? So these variables could be numerical, these variables could be categorical, etc. Correlation, as the word suggests, is describing the relationship between variables, right? Now, the best way, one of the ways to describe correlation is something called the Pearson's correlation coefficient, okay? Now, although I'm an engineer, I've done a lot of maths and so on and so forth. I love maths. The one thing I hate is formula. And, here is the formula if you really wanted to look at it. But as I've learned in all my sort of 18 years of experience, is that the formula matters less. What matters more is your understanding, your intuition, and the application of the data. So what I'll talk to you about really is not about how do you apply this formula and, how do you get to a certain answer, but how do you interpret this data, which will be useful for you from a problem solving perspective. Okay. So Pearson's correlation. So correlation, like I said, measures the strength of the relationship. The key in Pearson's correlation is a couple of things which I'll kind of underline over here. Is it measures the strength of the linear relationship between two continuous variables, right? So if you have two continuous variables, it measures the strength of the linear relationship between the variables. So if you have x and a y, and you have values of x and y in a table, right? You have values of x and values of y in a table. You could use this formula to come up with how correlated these two variables are. And the key bit over here that most people get caught up on is it's not just the relationship, it is the strength of the linear relationship between the two variables out here. Okay. So now why am I stressing on, linear, linear, and linear? So let's look at some examples out here. So the first thing is, if you look at Pearson's correlation, it varies in between -1 to 1. So it ranges in between -1 to 1. 0 could be one of the possible values when you apply that formula. +1 means the two variables are in lockstep with each other, right? They move in the same direction. So as x increases, y increases, right? As x increases, y increases. So a correlation of +1 means it's a perfect linear positive correlation that is going on between the variables. Now, in life, it's very difficult to find that, but for our purposes, we could say this relates to, let's say, for example, square feet of the house versus price of the house. Highly positively correlated. It's nearly impossible to find anything which is, +1 or whatever it is, right? So that is positive correlation. Negative correlation is where, so if you get to the other side, you swing the pendulum to the other side, -1 is where both the x and the y variable are completely moving in the opposite direction, right? So as x increases, y decreases. And just as a joke, this could be husband's opinion and this could be wife's opinion. As if husband's opinion moves in one way, wife's opinion moves exactly in the opposite way, right? So that's a perfect example of a negative correlation, just joking. But if you think about it, things like, for example, demand versus, price versus demand. So price is on the x-axis and demand is on the y-axis. As the price increases, like we discussed about, demand decreases. This is a good example of negatively correlated variables, right, that you could describe in here. You could also have zero correlation. So there is no correlation at all. So if it is zero, if the correlation tends to zero, it means that X and Y are not correlated at all, right? X and Y are completely not correlated at all. So it could be, for example, the amount of what is a good example? Whether Sachin scores a century in a game and the amount of rainfall in Delhi. Obviously, these two variables are not correlated at all. They shouldn't be correlated at all unless there's a case of spurious correlation. So there could be instances where there is no correlation at all between variables, right? Now, why is this useful and why are we doing all this, Gyan? The reason it is useful is because when we are trying to predict Y using X, correlation is a powerful measure to tell us whether X is a good predictor, bad predictor, or should be completely thrown away, right? So if let's say, for example, you're trying to predict the price of a house, you know that square feet of a house is a powerful predictor to include as part of your model. If you're looking at, let's say, for example, price of a product, you know that, sorry, if you're looking at demand, predicting the demand, which is demand forecasting, which pretty much every retailer, every bank, whatever it is, does, they know that one of the most important variables in prediction is price, and therefore price becomes an extremely useful variable when you look at the correlation. Now, no correlation is also very useful information, because if you're looking at predicting a Y, if you draw the correlation graphs or come out with a correlation in between different numbers, it will tell you which variables to completely exclude. So, if you have hundreds of variables that you typically do when you're running a machine learning model, you want to be running these what is called exploratory data analysis to understand what is the importance of this variable. And if you notice no correlation going on, then you know very quickly there's no use in using that variable for the purposes of prediction. All right. Now, so therefore, this is the understanding of correlation varying between -1 to 1. But there is one problem with Pearson's correlation and the way it is calculated, which is this particular graph, right? So, for example, there is a clear relationship here between X and Y. So X could be, let's say, for example, speed of the car. Y relates to, let's say, for example, mileage. And sorry, this is the ulta graph. This could be, let's say, for example, the amount of free time, like someone was mentioning. Sorry, I'll cut this. The amount of free time that someone was mentioning. Age versus amount of free time. And like someone said, that as age increases, the free time decreases, and then it increases after a point in time. You know that there is a clear relationship between X and a Y. However, if you use Pearson's correlation coefficient, if you use that formula, you're going to get a correlation of 3%, which is 0.03, right? So using just Pearson's correlation coefficient is not a great idea if a non-linear relationship exists between two variables. Every time a non-linear relationship exists between two variables, Pearson correlation kind of fails, which is why I keep coming back to the point that if you're looking to find out the relationship between two variables, it's important not just to look at the visual side of things or the numerical side of things. You've got to look at both to understand what is really going on here. Okay, so this is the limitation of Pearson's correlation coefficient. Any questions? And I'll take another 5 minutes. I know we're up for a break. Another 5 minutes, and we should be ending this. Okay. So question is, how do we solve for this? How do we come up with a good measure to numerically explain the relationship between variables if it is a non-linear relationship like this. And that's when your Spearman's correlation coefficient comes in, right? So what Spearman's does is it comes up with a modified formula that really measures the relationship between two variables that are related but are not linearly related. Okay, so Spearman's correlation coefficient does a far better job at measuring or giving you a numerical measure if the two variables are not linearly related. Now, how does it do it? Rather than using the Pearson's correlation coefficient, it first, for example, finds out the rank. Okay, so what do we mean by rank? I'll take a simple example to explain this. Imagine X has these values over here and Y has these values over here. Okay. So if you draw a graph between an X and a Y, so if X is 2, Y is, let's say, 21, X is 5, Y is 17, and so on and so forth, you'll get a graph which is something like this. You'll get a graph which is something like this. So this is not a linear graph. This is a non-linear relationship, and it is represented by this particular data in here. All right. So the first thing that Spearman correlation coefficient tells you to do in terms of the calculation, as it says, rank the data. Okay. So what do I mean by rank the data? Find out the first X data point. So the first data point has the highest rank. So when we mean rank, I mean, we take the highest value and put the value, give the rank over here. So for example, if you look at all these numbers, 3 is the smallest value, 21 is the largest value. So for 3, we assign a rank of 1, 5, which is the second smallest, we assign a rank of 2, 10, we assign 3, and so on and so forth, up to 6 over here. Okay. Second thing that we do is then apply this formula from a Spearman's correlation coefficient, which is sigma, x, y, all of that jazz, which I'll leave you to understand. But the point I want to make is the following. When you apply all this, you will get a Spearman's correlation coefficient of -1. What does -1 tell you? As X increases, Y decreases, or as X decreases, Y increases, which is exactly what you see in this graph over here. As X increases, Y decreases, X decreases, Y increases. Whereas if you would have run Pearson's correlation in here, it would have showed a small negative correlation because it's unable to pick up the non-linear part of the relationship in here. Okay, so that's the whole idea behind why we have Pearson's correlation, what is the limitation of Pearson's correlation, and then how does Spearman's correlation make it better when you have non-linear situations, right? So I'll go back and we'll kind of summarize what we've learned so far. So if you look at variables, we've looked at data which is quantitative versus categorical. And we've said the best way to describe the relationship is either visually or from a numerical perspective. So when we describe scenarios where it is categorical, quantitative, quantitative, and we said the most interesting thing to go after is really quantitative, because most use cases are based on that. We looked at how a scatter plot gives you a great idea from a visual perspective in terms of the relationship between variables. And we said if we were to describe it from a numerical perspective, first of all, if two variables are continuous, then Pearson's correlation coefficient describes the strength of the linear relationship. But if you have ordinal variables or variables that are not having a linear relationship, so for example, in this case, in this particular case, right? And in this particular case, Pearson's correlation coefficient might come up with a value which is very close to 0, which is very misleading. And therefore, you've got to use Spearman's correlation coefficient that will come up with a better value, right? So I know we have 5 minutes beyond the break time. So we'll take a quick break over here. So this is the first part of the theory. In the second part of the theory, we'll cover linear regression from a theory perspective. And in the last half an hour, we'll look at a quick case so that we firm up our understanding from both a theory perspective as well as a practical perspective, right? So I'll stop here. We'll take a quick break. We'll come back at 8:05. It's 7:55 right now. We'll come back at 8:05.
So you no need to leave the okay. Don't leave the link. Be here. You can take a break and you can join the same link again.
All right, hopefully you're back. We'll get started in 1 minute. Waiting for a few others to join.
Yes, sir.
Sir, you are mute.
Oh, sorry. Okay, we'll get started with the second part of the session, which is on regression. So let me quickly share screen once again. And if one of you could confirm, please, whether you can see the slides.
Yes, it's visible.
Okay, perfect. All right, so let's continue with our discussion. So we've discussed relationship between variables. Now it's a nice progression into regression. And again, without getting too complicated with the math, what I'd like you to first of all understand is the intuition with an example. So imagine you are in your company and the chief marketing officer comes to you and you're a data scientist and he says, hey, you know what? It's a recessionary environment, and my CEO is asking me to cut my marketing expense, right? Because we've got to save money. I can't, he's asking me to cut all my ad spend on TV or Instagram or whatever it is, right? And he says, can you help me with proving that the more we spend on marketing, the more sales we get? So you say, okay, I can, I attended this class and someone told me that if there are two sort of quantitative variables and you can draw a scatter plot and prove that as one increases the other increases. So imagine that you take data for the last few years and you plot marketing expense on the x-axis and sales on the y-axis, and it's a nice scatter plot. And you go and show this to the chief marketing officer and say that, hey, look, as the marketing expense increases, the sales increases, right? So he says, this is fantastic news. And he takes the scatter plot and he goes to the CEO and he says, look, here's what this is showing me. So the CEO says, it's okay, but you're not telling me what the scatter plot is really not telling me is that if I increase marketing expense by $1 or 100 rupees or whatever it is, how much will my sales go up? So now the chief marketing officer comes back to you and says, hey, can you help me? Because this guy is not satisfied with the scatter plot. He knows that as marketing expense increases, sales increases. Can you help me find out that with every increase in marketing dollar, how much the sales increase by? And that's where linear regression as one of the first algorithms in machine learning. By the way, machine learning has existed, as you know, for 50, 60, 70 years, just that in the last 20 years, because we have to pay people a lot of money and we have to give people fancy titles, we're calling it machine learning. But anyway, linear regression has existed for a very, very long time. So linear regression, very simply then, is to explain the relationship between a dependent variable and an independent and one or more explanatory variables or dependent variables, right? So what this very simply means is that the dependent variable over here is sales. So sales is dependent on marketing expense, and simple linear regression is essentially explaining the relationship between sales and marketing, right? You could take the same thing and you could say this could be price of the house versus square feet of the house. This could be, for example, the Y variable could be cholesterol versus weight of the person, and so on and so forth. Right? There could be a million other examples where you could easily explain, the relationship between a dependent variable and one or more exploratory variables. Simple linear regression is where there is only one explanatory variable. So for example, in this case, marketing. All right. So remember, what was the chief marketing officer telling you? Can you tell me for every increase in marketing dollar, how much is the increase in sales? So imagine you have this scatter plot, which is with this marketing expense, I get this sales, this marketing expense, I get the sales, and so on and so forth, right? So I'll kind of get rid of this. And now there are two ways to solve this problem, right? There are two ways to solve this problem. Either you become very cute and you basically start drawing a curve, which is this. Okay, so you come up with an equation which says that y is equal to, a of x plus b of x square plus c of x cubed. So you make it a polynomial equation, and then you go back to the marketing guy and say that, look, this is the equation basis the data that you have, and therefore if you start plugging in the values, you will get the value of y. So depending on what the value of x is, you'll get the value of y. However, this is not a great way to do it, because you know that it's not a very clean relationship, right? In the sense that even if you use this equation, it is not like in the next year me and you know that in real life it doesn't fit perfectly to this equation. So you might have, basis this equation, you might predict that the sales goes up to this. In reality, the sales might be this, right? So for you to play safe as a data scientist, you don't want to give a very, very precise answer. And when you get into machine learning, you will hear about this concept of overfit, which is you are overfitting the data and you're coming up with a very precise equation that you know will never work in real life, right? So in order to play safe as a data scientist, what you would do typically is you will say that instead of plotting this as a very complicated polynomial, you will plot it as a very simple line, and you'll say that the relationship between y and x can be described in form of a line, and that line very simply becomes y is equal to mx plus c. Why is this equation y is equal to mx plus c? Because remember, when we were small in our whatever 8th, 9th, 10th class, now I forget which class, these days they're teaching this in like 3rd class, I believe, but whatever. So we've learned the fact that given a y and an x, if they are linearly related, they can be described with this equation, which is y is equal to mx plus c. Now, in statistics and machine learning, we like to complicate things a lot. So what we do is, instead of m, which is the slope of the line, we are calling it beta 1. Instead of c, which is the intercept, we call it beta naught. If you see some literature, they also write it as y is equal to wx plus b, where w is the weight and b is the bias. Typically useful if you're doing things like deep learning and stuff like that. But at the heart of all of it, it is really the equation that we have learned, which is y is equal to mx plus c. Now the reason, so this is the simple equation, right? Y is equal to mx plus c is the equation that we learned in school. Now the reason we can't use very simply y is equal to mx plus c in this case is that, looking at this graph, this line over here is described as y is equal to mx plus c. But let's say, for example, you've spent this much on marketing. If you plug that number over here, it will say that your sales is this, right? Similarly, if you spend this much on marketing using this equation, it will say that sales is this, and so on and so forth, right? But you know that the real sales in this case has been this, the real sales in this case has been this, and so on and so forth. In other words, you know that even with this equation, there is an error term that is occurring at every point. And this error varies depending on which point you're talking about. So for example, the error here is E1, the error here is E2, the error here is, let's say, E3, the error here is E4. It's a variable error term. Depending on the data point, you could have a different error. So what you would do to describe the relationship between a y and an x is you will modify the simple equation that you learned in school, which is y is equal to mx plus c, and add an error term out here, which is epsilon, and we are calling it a random error because depending on the data point, the error can be very different. So it is randomly varying. All right. So just to summarize, simple linear regression describes the relationship between two variables. In a very happy world, you could have described it as y is equal to mx plus c. In, like I said, in machine learning, we call it beta 1x plus beta naught, which is beta 1 is m and beta naught is c, which is the slope and the intercept. The reason we can't use this very simple equation is because we know there is an error component. Even if we say this line is the relationship, we know that there is an error component. And that error is then described by this epsilon term, which is randomly varying basis the data that is here. Okay. So let me pause and see if someone has any questions in terms of understanding this.
So that epsilon value is always absolute value, or it can be positive or negative?
It can be random. It is, so it's a random variable, right?
Variable.
So it will keep varying depending on what is the value of xi. So for this, so if I remove all this for a moment, for this xi over here, right? For this xi over here, the error is E2, which is this error. For this xi over here, the error is E1. So depending on the data point, this error varies all the time. That's it. Make sense? Okay. All right. So now, point is, you want to be, as a data scientist, you want to be as exact as possible in terms of the relationship, which means you want to come up with the best possible equation that describes the relationship between y and an x. Okay. So in other words, if I remove all this for a moment, the best line that I can come up with is the line that minimizes the value of this error. Let me repeat. The best line that describes the relationship between y and x is the line that minimizes the value of this error. Okay. So what will you do? What you will do is you will draw all sorts of lines, right? You will draw all sorts of lines. What do I mean by drawing all sorts of lines? Each of these lines has a slope beta 1 and an intercept which is beta naught. So with each of these lines, you will draw different lines with different slopes and different intercepts, and what you will see is which is the best fit line that produces the minimum value of this error. Again, just to repeat, you will draw multiple lines and you will find out that line that throws out the minimum value of this error. In other words, you are trying to find out which is the best fit line, which is the best fit line. Okay. So there are multiple lines that you could draw in order to describe the relationship between y and x, but the best fit line is the one that minimizes the value of this error. In other words, you have to find out the right beta 1 and the right beta naught that minimizes the value of this error. So you've got y and you've got x, right? Y is the sales that was generated. Y is all the marketing spend that was done in the past. And the whole point of linear regression is to find out the best slope and intercept that minimizes the value of the error. That's all there is to linear regression in a way. Okay, find me the slope, find me the intercept, that minimizes the value of this error. So find me the best fit line. So question is now, how do you find the best fit line, which is the next slide, right? So if I remove this, so question is, how do I find the best fit line? Or in other words, how do I find the best values of beta naught and beta 1? So that is what we will describe over here. Okay. So the way to do it is called the least squares method. The least squares method. Okay. Now let's think about what is the least squares method. All right. Now remember I said in order to find the best fit line, you can draw multiple lines. You can draw multiple lines. Okay. So imagine one such line, which is this blue line that I drew. Okay. Imagine one such line, which is the blue line that I drew. So for this blue line, what you will do is you will find out the total error that is being generated for this blue line. So for example, the error over here is this is actual minus predicted, let's say E1. This is actual minus predicted, let's say E2. This is actual, this is predicted, this is E3. Actual, predicted, E4, and so on and so forth. So one thing you could do is for this particular line, you could say, I will sum up all the errors because I want the total error to be minimum. So I'll do E1 plus E2 plus E3 and so on and so forth. Now, what is the problem with doing this? The problem with doing this is you might end up canceling the errors. So for example, the error. So how do you define the error? The error is actual value minus predicted value. Okay. So here the actual value is greater than the predicted value. So let's say, for example, theoretically, this is plus 5. Okay. Here, actual value is less than the predicted value. So according to this, this might become minus 3. Here, this might become plus 2. Here, this might become minus 1, and so on and so forth. Now, the problem with using this formula, which is total error is equal to sum of all these errors, is that if this is plus 5, minus 3, plus 4, minus 6, and so on and so forth, these errors might end up canceling each other. Therefore, you cannot use this formula in order to find out the total error. Just to repeat, error is what? Actual value minus predicted value. So actual is here, predicted is here. So this is a positive. Here, actual minus predicted is a negative. So if you use a simple formula which says that it is E1 plus E2 plus E3 plus so on and so forth, you might end up canceling all of these errors, right? Now, therefore, this is a wrong way of doing it, okay? The right way, therefore, in order for all these errors to not cancel each other is to sum of squares of all the errors. So let's focus on this formula, which is this is your actual, this is your predicted. So this becomes the error at every data point. So let's say, for example, this is E1. In order to prevent the cancellation effect, you will do square of this and you will do sum of squares. So what essentially it means is E1 square plus E2 square plus E3 square plus so on and so forth. So sigma sum of squares of errors so that it doesn't cancel each other. And then if you want to find out the average error, you divide that by the total number of data points that is here. Okay, so this is defined as MSE, which is mean. So this is the mean part of it, square, which is this part of it, error, which is this part of it. So you're doing sum of squares of errors divided by the total number of data points, which gets you to MSE, right? So the best fit line, is the one which has the least MSE. The best fit line has the one that has the least MSE. So just to summarize, if you define total error as sum of the errors, it might get cancelled. which is why you do sum of squares of errors of every possible line that you could draw. And the best fit line is the line which has the least MSE. That is why it's called the least squares method, because you're finding out the least MSE. Okay. Does it make sense? Any questions on this? All right. So now let's also not lose track of the bigger problem that we were trying to solve. What is the bigger problem that we were trying to solve? The marketing guy came and asked us, for every increase in marketing spend, what is the increase in sales? So for you want to find out how sales is connected to marketing spend, where X becomes your marketing spend. Okay. And you know there is an error component, but using the best fit line, you're trying to minimize the error component. So you're trying to find out through the best fit line, what is the beta naught and what is the beta 1 over here. So the point very simply is you run all this math and you come up with an equation that says sales is equal to 1000, which is, let's say, this intercept. And I'm making up random numbers out here. Imagine you've run this equation and you've got beta naught is 1000, beta 1 is 200 into marketing spend. So what is this telling me? So this is important to understand from an interpretation perspective, because most people lose sight of this because they get lost in the math, right? So what is this telling me? For every dollar that I spend in marketing, I am going to get an incremental 1000 plus 200, which is $1,200 in sales. Okay, for every dollar that I spend in marketing, if this is the value of beta naught and beta 1, which is the best fit line, I will get a 1200 increase in sales. So imagine you go to the marketing guy and says, hey, for every dollar you're getting additional $1,200, he'll be like a super happy guy, right? Imagine your equation said sales is equal to minus 1000 plus 200 into marketing spend. So what does this equation tell you? For every dollar that you spend in marketing, your sales goes down by minus 800. If you present this to the marketing head, he'll say, you're a bad data scientist. I don't need your services anymore. I will do my own thing, right? So this is why linear regression is so powerful and so easily interpretable to the business, because it tells you very quickly what is the impact of X on Y over here. Okay, so that's the whole idea behind linear regression.
One question I have.
Yeah, sure.
So, yeah, so for canceling the error, we have used MSE, right? We can also use mean absolute error.
Absolutely. Yeah.
Yeah.
Great question. So the reason we don't use mean absolute error, so just to explain the point a little bit, is if I remove this for a moment, we could use instead of E1 plus E2 plus E3, which cancels out the errors, we could use absolute E1 plus absolute E2 plus absolute E3, is because if you think about it, the way this is solved internally. Now think about it, we can't draw hundreds of combination of best fit lines, right? So the way to solve this problem is using a method called gradient descent. Okay, what we do is we take an equation and differentiate it. And why we use MSC over this is called MAE, mean absolute error. The reason we use MSC instead of MAE, because MSC is easily differentiable as compared to MAE. That's the whole reason why we use MSC. Make sense?
Yeah, thank you.
Okay. All right. Any other questions on linear regression and the interpretation of linear regression? Okay, all right. So then let's go to the third part of the theory, which everybody loves as far as linear regression is concerned. So everyone talks about this term called R square, R square, R square, R square. If I ask most people when I conduct an interview, I say, what is the definition of R square? Immediately they will tell me this formula, right? R square is equal to 1 minus SSC, sum of squares of regression divided by sum of squares of total. And I tell them, I don't get the math. You explain to me what it really means, right? And here is the real interpretation of why R square is so powerful. Okay. So R square, by the way, for those of you who haven't heard it before, is a metric that talks about how good your model is. How good your model is, right? How good your model is, meaning that, in other words, your model has been able to minimize the errors to a significant extent. If you want a more formal definition of what is R square, it is very simply the amount of variance of y, which is the dependent variable, that is explained by x. That is explained by x. For me, even this definition is a little confusing. What does this actually mean, right? So in order to understand what R square really means, and for me, if something is not simple, I don't get it, right? So let me explain what R square really is and why R square is so powerful when it comes to linear regression. Okay. So imagine someone asked you to predict something. So let's say, for example, the Y that you're predicting is the house price, and you are given data around square feet of the house, and you're given a new data point over here, and you are asked, given this historical data, can you tell me what is this house price over here? All right. And imagine that you had no idea at all of linear regression or anything in machine learning in terms of prediction. So if you asked a random person who knows a little bit of math in order to predict the price of the house, the most reasonable way to predict the price of the house is using the average, which you learned, I think, in the previous session. So if you knew nothing at all, and let's say, for example, I ask you, what is Virat Kohli going to score in the next match? I am sure 99.99% of us are not going to apply a linear regression and say that, hey, basis all these variables, this is the score, right? We are just going to look at the average score that Virat Kohli has scored and say that here is the average score that Virat Kohli would score. Very similarly, if I were to ask you what is the house price, and if you didn't know any technique at all, the simplest technique that you will default to is the average. So this is the average. So this is what I call the dumb model. Okay, the dumb model, which is you didn't need to know machine learning. You just say this is the average house price or whatever it is. So the point over here is any model that you build has to be an improvement over the average or over the dumb model. If your model is not doing even as good or as bad as the average, then you have really done a bad job, is the idea over here. So R square tells you how much better you are as compared to just coming out with the average. Okay. So now let's focus on the formula. What is SS total? SS total is the sum of squares of errors of this particular line. So what is the error of this line? The error of this line is this, 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 error of this line is this. Okay. So this is the sum total of, what do you call, the errors that have come out of this particular line over here. Okay. What is SS regression? SS regression is the sum of squares of the residuals over here, right? So it is this error, this error, this error, this error, this error. If your model is good, if your model is good, this will be close to zero. What do I mean? If your model is good, the errors of the model will be nearly zero. If your model is fantastic, this value will be zero. But if your model is good, then it will be close to zero, right? So something which is close to zero divided by this value, this is close to zero. Okay. So what is this formula telling you? R square is 1 if your model is fantastic. On the other hand, if your model is as bad as the average line, that you have done nothing and your model is producing the same amount of error as the average line, this divided by this, because whether it's your model or whether it's the average line, it is producing the same amount of error. So this divided by this is 1 because the error is the same. 1 minus 1 means r square is equal to 0. R square is equal to 0 means you've done such a terrible job that you haven't been able to even beat the average prediction out here. So which is why R square varies between 0 to 1. All right. Now, theoretically, if you think about it, there could be a case where the sum of squares of regression is actually greater than sum of squares of average, which means that this is greater than 1. It could be 1.2. So theoretically, right? So 1 minus 1.2 makes it minus zero point 0.2, which means that you have done an even more terrible job than what the average line could do, and you should just give up your career in data science or whatever it is, right? So that's the whole idea around R square. So if R square is 0, it means it's a terrible model. R square is equal to 1 means you've done a fantastic job. Usually R square varies in between 0 and 1. So higher is the R square, better is your model. And again, just from experience, I'm telling you, if it's in retail, if R square is anywhere greater than 0.7, zero point 0.8, it's a respectable model. But in the medical field, even if you have an R square of 0.3 or zero point 0.4, it's a decent enough model to start with, because typically medical related problems are tougher to solve. So even a lower R square is much better from that perspective. Okay. So any questions here in terms of what is R square? If R square is high, it means it's a good model. R square is low, it means it's a bad model. And what is the interpretation really of that? Okay, so that's R square. And then finally, yeah, anyone has a question? I can't see the screen, so please speak up. Okay, all right. Finally, the idea here is, again, let's think of the marketing guy and your chief marketing officer and the CEO. So your marketing guy takes this wonderful equation that you have come up with, which is y is equal to 1,000 plus 200 into marketing spend. And he takes this equation to the CEO and he says, see, I told you every dollar you put into marketing, I'm going to increase your sales by 1,200. And is the CEO obviously is the CEO. He gets very suspicious. Then he comes back to you and he says, boss, it is not that sales is just a function of marketing, right? Because if you keep putting money into marketing, it will keep increasing. In reality, the sales is probably a function of not just marketing. It's a function of how the economy is doing. It's a function of how many staff you have in your stores. It's a function of whether it is, so economy is recession, it's a function of how many staff you have in stores. It's a function of the price that you're providing. It's a function of the service that you're providing, and so on and so forth. So he comes back to you and says, boss, I know this. Rather than just focus on marketing, can you build me a proper equation, a real life equation that explains the impact of every variable on the dependent variable? And what you've just done is talked about multiple linear regression, right? So the idea here is, rather than looking at only the effect of one variable, you understand the effect of multiple variables. For this, none of the theory changes. The explanation is exactly the same. You still use the least squares method to find out the best fit line. In this case, it's not a line, it's a plane, because if you can imagine, and that is why we're not doing any graph here, it's not a line that connects a y and an x. You now have x1, x2, x3, x4, and so on and so forth. It becomes the best fit plane, which is multi-dimensional plane. But the way you do it is exactly using the least squares method or gradient descent or whatever it is, in order to find out what are the right values of beta, b0, b1, b2, and so on up to bn. So at the end of the day, after having spoken to the CEO, you will come up with an equation which says sales is equal to, I'm making it up, 200 plus 10 into marketing minus 5 into, let's say, for example, your cost plus 10 into the amount of staff that you have in stores minus, for example, the debt you have, and so on and so forth. So your CEO will look at this equation and say, aha, so if I reduce my cost by a certain amount, I can actually increase my sales. If I increase my staff, I can increase my sales. So this becomes the various levers that the CEO has, and he can pull in terms of understanding, how he can increase or decrease. So why linear regression is so very powerful is because, one, it understands the relationship between the different variables. Two, from a real life business scenario, it gives you levers to pull, and you know exactly to what extent you can pull these levers in order to influence the dependent variable. So this is the whole idea of multiple linear regression. Otherwise, everything remains the same. Your R square remains the same. How you find out using gradient descent, the best fit plane, etc., remains exactly the same. Okay. So any questions out here? Anything on this? Okay, assuming that was clear. And then finally, let's come to the use cases. So if you think about it, the use cases are multiple. You find out you can find out the impact of marketing spend, price, promotion on sales, which we does.
Excuse me,
Yeah.
sir. There is okay. One ma'am have raised his hand. There is a
Okay.
question. There is a question actually.
Oh, sorry, I can't see the screen. So if you have a question, please speak up.
Yeah, you can speak. You can just unmute yourself and you can talk. Okay, I'll read out the question. It is in the chat box.
Sure.
So in case of like Alzheimer's disease diagnosis, is this R square value to be considered as parameter apart from MMSE?
Yeah, R square is, yes. So not just Alzheimer's, but any other model or whatever it is. R square is a simple way of talking about whether a model has worked or whether a model has not worked. So if you talk about MSE, which is mean square error, right? This mean square error can have any set of possible values. It can be 1,000, it can be 2,000, it can be 3, it can be 5, it can be whatever, right? The point is, it's very difficult for the business guy to understand. If you tell him the MSC of this model is 1,000, he doesn't know whether it's good, bad, ugly, whatever, right? But if you go back and tell the business that your R square is 0.8, the intuitive understanding of this is that 80%, the model is nearly 80% there, right? That's the simple intuitive. That's not, by the way, let me caveat that by saying that is not exactly what R square is. But if you go back and tell the business that the R square is 0.8, it provides a reasonable confidence, because in the business's mind, it's like, the model is nearly 80% there in terms of accuracy, right? Whereas compared to MSC, MSC is a value, you really can't interpret it from that perspective. Okay, hope that helps. All right. So in terms of use cases, like I said, we talked about predicting price of house and real estate. So if you model this as a linear equation, a linear regression, essentially it becomes price of the house is a function of beta naught plus beta 1 into square feet of the house plus beta 2 into, let's say, for example, number of rooms in the house plus beta 3 into the location of the house, and so on and so forth, right? So that's the second use case. In the insurance industry, you want to predict the number of claims that is made by an individual. So you can model that as beta naught plus beta 1 into income of that individual, how many times he's claimed in the past, what vehicle he drives, if it's a car insurance, where does he live, because there are zones where there is a higher chance of a claim versus a lower chance of a claim, and so on and so forth, right? And then, this is a practical use case that we actually worked on in my previous company at Tesco. So they wanted to understand, if customer satisfaction is your Y variable, which is the biggest lever that they can pull it to increase customer satisfaction. So we built an equation which basically said that customer satisfaction for online deliveries is a function of time of delivery. So the time of the delivery, so whether it was late or not, beta 2 in terms of communication, Beta 3 in terms of the driver and the appearance of the driver and the hygiene of the driver and so on and so forth, because it really matters when we are talking grocery deliveries that are being delivered to the doorstep and into the house. Beta 4 into size of the order. So, do higher size orders have lower satisfaction and so on and so forth. And the ultimate analysis or the ultimate conclusion that we came was that communication really matters, right? When we do online deliveries, if you think about it intuitively, it makes sense. If you're getting late, if the company communicates that's getting late, it reduces the anxiety for people and that makes it better. If you don't communicate, you're going to have thousands of calls coming into your call center and the customer is going to be really angry and the customer satisfaction is going to drop. And therefore, communication turned out to be actually one of the biggest variables in order to improve customer satisfaction in there. Okay. So that's very quickly, linear regression theory. So if there's no other questions, we can take a quick break and then I will show you a very quick case study on Python just to bring all of this theory together. Quick, simple case study. Any final last questions on the theory? All right, guys. So we'll take a break here. I think it's a good time to take a break. So it's 8:46 by my watch. We will reassemble at 9. And like I said, I'll show you a quick case study for half an hour and we'll wrap it up at 9:30. All right. So break until 9 p.m.
Yeah, okay. So be there. Okay, you can join again at 9. Don't leave the link. Okay, the same link, the recording will be on. Don't leave. So we will be joining again at 9. If you have any queries, you can put it in the chat box. I'll compile it and I'll ask to the resource person.
All right, we'll get started in exactly 1 minute. All right, let's get started. So for the final section, what we'll be doing is a case study on linear regression, just to bring all of the theory together that we've learned in the last couple of hours. So I'm going to share my screen. Um, Hopefully you're able to see my screen. Can one of you confirm, please?
Yes, sir.
Okay, perfect. All right. So we will cover a case on Python. The idea here is not to go through the code. I know some of you are not as familiar with Python, and you have an entire session on Python for next week and stuff like that. So what we'll do here, and what I'd like you to really focus on, is the case at hand and what is the interpretation of the data over here. If you do that, that's more than enough. I don't expect you to go through line by line and understand it, because if you're not familiar with Python, this is obviously going to take a lot more time, right? So focus on the understanding, focus on the case, and you should be fine. All right. So what we're doing over here is we are constructing a simple linear model that explains the relationship between a car's mileage and its other attributes. So why is this important? Because car manufacturers all the time are thinking about how do you improve the mileage of a car. You know the famous statement of everyone goes into Maruti and says kitna deti hai. So everyone wants to keep increasing the mileage of the car, and they do things like making the car lighter, which is very dangerous. But that's a separate topic for another time, right? So what we'll do is understand the relationship between mileage and other attributes, and see how much each of these attributes has an influence on the mileage out here. So the first step over here is to import a set of packages. The reason why Python is so powerful as compared to some of the other languages is because you don't have to write code from scratch. So for example, if you have to, come up with the formula for mean square error or R square or whatever, Python allows you to do that in a single line of code by pulling what is called packages. So these are ready-made codes that are available that you can just reference for whatever you need. So these libraries are packages that kind of contain everything that you want from the perspective of ML, linear regression, whatever it is. So this is what we are doing over here, which is we are importing all the packages that we need. And like I said, I won't go into the detail, but just think of it as these are ready-made packages that are available for you to use for whatever you have to do. All right. Now, what we will do is we will import the data set. So the data is auto.csv. It's a CSV file. In fact, I think I can. Anyway, we can look at the code itself and do it. So this is a CSV file that contains information about auto. Actually, let me just pull it up. Auto.csv. Yeah. So as you can see, this is the data set. It contains information on miles per gallon. So this car gives us 18 miles per gallon. Cylinders. So this consists of 8 cylinders. Displacement. So displacement essentially is, so we say, for example, it's a 1.5 liter engine or a 2 liter engine or whatever it is. So this is what the displacement is. This is obviously an old data set, therefore the displacement is lower. The weight of the car, so this is 3504 kgs is the weight of the car. And then the acceleration of the car, so how quickly it can accelerate is the whole idea around here, right? And so the idea is, how do you build a linear model that has miles per gallon as your dependent variable, which is the y variable, and everything else as the X variable to understand whether a cylinders has an impact, displacement has an impact, and if it does have an impact, then what is the impact of it, right? That's the whole idea over here. So the start to any problem is to start with your hypothesis, right? So for those of you who are familiar with cars and how, mileage and cars operate and stuff like that, can someone tell me, as the weight increases, will the mileage increase or decrease?
Decrease, sir.
Decrease, right? Heavier cars typically have lower mileages, which is why, I mean, if you think of Innova might be a bad example, but if you look at Tata Harrier versus, let's say, for example, smaller car like Maruti, obviously the Maruti smaller car, lighter car is going to have, much better mileage. What about displacement? So do you think a 2-liter engine or a 3-liter engine will have better mileage or a worse mileage as compared to a 1-liter
Again,
engine?
again, inverse case. As
Again, inverse case.
yes,
Again, inverse case, unless you're using a turbo engine that these guys talk about. All right.
yes.
Similarly, acceleration is supposed to have a negative impact, but we'll see, right? And similarly, cylinders, the more the cylinders, the more power being generated, all of that stuff, right? So why I say start with the hypothesis is because if you do the analysis, if you do the visual representation of the data, and you notice that what your hypothesis is versus what you see in the data is opposite, then it means two things. Either you have imported the wrong data, or there is something that you don't know. And therefore, you'll have to go back and ask the business about, hey, I'm finding some funny thing here. Can you tell me why it's happening? And they might say, hey, even we didn't know that. Or, yeah, that is explainable because of XYZ. So if you start with any machine learning problem or whatever problem that you have, always start off with a hypothesis so that you can validate it. When I mean validate, I don't mean running hypothesis tests. I mean, you can validate it visually or numerically and then understand what is actually going on. So this is the table that we have imported into Python, and that's the code that we have typically run over here, right? So we've taken the CSV, we have read the CSV and converted it into what is called a data frame. Data frame is a data type that Python understands. Think of a data frame as a simple table. So when you run this code, if I run this code, right, I have to import all these packages once again. Hopefully I've imported auto.csv over here. Yes, I have. Okay. Yeah. So once I've imported the data set, it's telling me that the shape of the data set is 398 into 5. What this means is there are 398 rows and 5 columns in this data set over here that we are analyzing for today. So we look at the top 5 rows just to see if we have imported the data set correctly, there are no errors, etc. And just to understand what the data set is about. So what you can do is you can say data frame.head. This will tell you, this will give you the top 5 rows of the data set. So as you can see, the first 5 rows come out: miles per gallon, cylinders, displacement, weight, acceleration. And the reason you do this, like I said, is two things. One, you check whether the data imported is correct. And secondly, you just get a sense of what the idea, what the data set actually looks like. Okay. So remember, I said in relational analysis, you want to do two things. You want to understand the visual analysis, so draw graphs, draw plots to understand how the data is behaving visually and what is the relationship that is being seen. And then you want to also come up with a numerical sort of analysis to just validate what you're seeing visually in there. So first thing that we will do is run plots on this data. Okay. If you're not familiar with Python, don't worry, but this is one of the most powerful plots that we use in Python. It's called pair plot. So what does a pair plot do? It takes every variable and compares it against every other numerical variable in the data set, right? So it takes every variable. So think about it. So there's miles per gallon. It compares miles per gallon against cylinder, against displacement, against weight, against acceleration. Similarly, cylinders against displacement, cylinders against weight, cylinders against acceleration. And it draws the graph of all of that. And in one shot, you are able to look at the visual representation of the data. Okay, so let me explain how to read this. If you look diagonally, it is the variable against itself. So for example, this graph over here is miles per gallon against itself. So this is the distribution of miles per gallon. So this is, you can call it univariate analysis, variable against itself, right? Similarly, this is number of cylinders against itself. So if this was blown out a little bit more, you would see that there's 2 cylinders, 4 cylinders, 6 cylinders, and 8 cylinders. Okay. Similarly, this is displacement against itself. Looks like a lot of the displacement is towards the lower end of the data, and so on and so forth. But what is more useful for you is the bivariate analysis. So how do I read the bivariate analysis out here? You take miles per gallon and you look at this graph. So the y-axis is miles per gallon and the x-axis over here is the displacement. Okay. So if I come to this graph, miles per gallon is on the y-axis, displacement is on the x-axis. And what this is telling you is that as the displacement increases, miles per gallon reduces. It's not a perfectly linear relationship out here. It's not a perfectly linear relationship out here, but it is what we said in our hypothesis, right? Which is that as displacement increases, as you go from 1 liter to 1.5 liter to 2 liter, it's a heavier engine, and therefore your miles per gallon kind of reduces. Similarly, since miles per gallon is the most interesting variable, that's what we are comparing against. So let's look at this graph. What is this graph saying? It's miles per gallon on the y-axis, and the x-axis is weight of the graph. No, sorry, weight of the car. So again, as expected, as the weight of the car increases, miles per gallon drops, right? Again, expected, not so much of a surprise over here. But the final thing is a little bit of a surprise, which is, let's look at miles per gallon against the last variable. So what is the last variable? It is acceleration. So what this is saying is actually there's no real relationship. I mean, if you see, there is almost like a low or not too much of a correlation going on over here between miles per gallon and acceleration. So this graph tells you that actually the relationship, even if the correlation value comes out to be whatever, -4, -5, whatever, -0.4, -0.5, whatever, the relationship is not actually very strong, as strong as it is in this graph or this graph. So just from this one plot, you will be able to say the two variables that seem to influence miles per gallon the most are displacement and the weight of the car rather than the acceleration. I think somebody had a question. Somebody unmute. Okay. So I'll give you, instead of going through graph by graph and explaining this, I'll give you another explanation of this, and I'm happy to share the code. You can look at it yourself. So if you look at displacement versus, let's look at what this variable is, weight. Okay. So what this is saying is displacement is on the y-axis, weight is on the x-axis. And again, not surprising, as the displacement goes up, as the weight goes up, the displacement goes up. Heavier engines have higher displacement. Heavier cars have higher displacement, which is not surprising, because if you think of an Innova, has a 2-liter engine. A Maruti used to run on 800cc, now it's a 1-liter engine, right? So again, not surprising that you found this relationship. What is important, which we don't have the time to go through, but I'm sure you'll talk about it in the future sessions, is that these variables might suffer from a problem called multicollinearity. Multicollinearity is a problem when it comes to linear regression. Again, we don't have the time to go through that. Multicollinearity just starts producing funny results in your model and should be eliminated. So if I were doing this in real life, what I would do is I would actually pick only one of these variables, because very simply put, the information in one variable is contained in another variable. So if you include both these variables in here in building your model, you're actually double counting from that perspective, right? So that's the kind of interpretations that you could really draw out of, all of these models out here, right? That's the idea. Okay. Any questions so far in
So,
terms of understanding? Yeah.
sir, in this case, there are total 25 graphs, means 5 by 5.
Yes. Yes.
So,
Yes.
upper triangular graphs and lower triangular graphs are symmetric, no? Means
Exactly. They're opposite of each other, right? So
okay.
this is MPG versus MPG, MPG versus what is this cylinder. So if you look at this graph and you look at this graph, these are mirror images of each other because this is cylinder against MPG. If you look at, let's say, for example, which graph and which graph. So if you look at displacement versus whatever cylinder, and cylinder versus displacement, these are mirror images of each other, right? So you'll have a lot of graphs that are repetitive. It's just turned in another way. That's all. Does that make sense?
Yes, sir. Yes, sir.
Okay.
Got it.
Okay. All right. So this is giving you the visual representation at this stage. The conclusion that you're drawing is MPG, which is the dependent variable, is dependent mostly on the number of cylinder, sorry, on the displacement and on the weight of the car. This is powerful information as you get into modeling. Now, like I said, like every doctor, they don't just visually examine you, they also look at the temperature, blood reading, all of that stuff. We will also look at this graph in terms of the numerical analysis where we will do correlation, right? Correlation over here. And what I've done is to create a simple heat map for the correlation, okay? So what this beautifully does is it gives correlation between the different variables. So you see miles per gallon over here versus displacement is minus zero point -0.8. This is very close to -1. What is this telling you? That as displacement increases, miles per gallon decreases, which is exactly what you saw over here. Which is exactly what you saw over here. Yeah. Similarly, miles per gallon versus weight minus 0.83, which is what you saw over here, right? Negatively correlated, and so on and so forth. Similarly, I said that if you look at this graph, which is displacement versus weight, right? Looks like a very nice linear relationship, which is dangerous because if independent variables are correlated to each other, it might lead to the problem of multicollinearity. This is also confirmed by this displacement versus weight has a correlation of 0.93. This is not good news for you when you're actually building the model. And I'll show you because of this, actually R square drops by a bit. Okay. So we don't have time to get into what you can do. Like I said, I mean, if I were building the model, I would typically do a technique which removes this. We could use, principal component analysis, whatever it is, but that's kind of out of scope for this class that we're discussing. But in real life, you will treat this. You will not let it go like this, right? But this is simply put the visual as well as the numerical analysis of all of these variables. Okay. Then what we will do is enter into the actual linear regression code. So what we will do is the following. So I'll kind of draw it out over here so that it's very clear for you. So I'm going to clear this. Okay. So in machine learning, there's a process that we follow, which is we take all the X variables and put it into one data set, and we take all the Y variables and put it into another data set. Okay. Now, further, we will split X into X training and X test. Similarly, your Y variable, which is MPG in this case, and X consists of all your displacement, weight, number of cylinders, all of that stuff, right? So this is what I mean. So Y also, you will split it into Y train and Y test, right? Now, what you will do is in machine learning, you have to build the model and test the model. You will build the model on one data set and then test it on another data set to prove that the accuracy of your model is great. So it's almost like if you go back to your 10th class board exams, you used to have model papers before you know, the final board exam, like these practice papers, model papers, or whatever it is that your school used to conduct before you actually went for the board exam. So the whole idea over here is you would train the 10th class student on one data set and then test the 10th class student on the board exam. That is exactly what you do in machine learning, right? So you will build a model on the training data set and you will test it on the testing data set. So you will combine X train and Y train and build the model. All right. Once the model is built, what does the model give you? The model gives you the relationship between X and Y. So beta naught plus beta 1, X1 plus beta 2, X2 plus so on and so forth. So when you take X train and Y train and build the model, it will give you the values of all this beta naught, beta 1, beta 2. Now, what you will then do to prove that your model is good is that you will use X test. You will use X test and feed the X test into each of these X's over here. So you'll use X test. And since this model is built, you will feed X test over here. And when you feed X test over here and you use this equation, you will get Y predicted because you're taking X test, putting it into the model, and the Y is outputted, which is the Y predicted. So what you will then do is to compare Y test and Y predicted to calculate things like MSE, R square, all of that stuff, root mean square, and all of that. Okay. So just to repeat, this is standard for any machine learning problem that you're doing, which is supervised machine learning. There is Y, there is X. So you split X into X train and X test, split Y into Y train and Y test. Use, so maybe I'll color this way, use X train and Y train to create your model. Use X test, feed it into the model, get Y predicted, compare Y test and Y predicted. In an ideal state, they should exactly be the same, but obviously it's not going to be the same. There's going to be an error. So you calculate MSE and R square, and the model that produces the lowest MSE or the highest R square is the best model or the best fit line or whatever you want to do. Okay, so that's the idea. So if you now look at the code, any questions on this, by the way? Okay, so if you now look at the code, so that is what we're doing. So the first thing is we are splitting the data. So we're taking all the X variables and moving it into a data frame called X. All right. We are taking the Y variable, which is MPG, and putting it into Y. Okay, so this step, which is the first step, putting all the X variables into X and Y variable into Y. Second thing is we will split the data set into training and testing. So there is this package that takes your X and Y, that takes your X and it takes your Y and splits it into X train, X test, Y train, Y test by saying that the test size is 0.3. What is the meaning of test size is equal to 0.3? It means 70% of the data is training and 30% of the data is test. In other words, you will use 70% of your model to 70% of the data to build the model, and the 30% which is a holdout is where you will test to see if the model is producing accurate results. So that is what it means by test size is equal to 0.3 over here. All right. Then what you will do is you will fit the linear model. So like I said, in Python, everything is a single line of code. So linear regression, you don't have to write any formula, nothing at all. You will just call linear regression package. You will fit the model. At the end of this step, the model is built, right? So which is why I say,
Sir,
yeah,
can I know about the random state equals to 1? Why we took it like that?
okay, great. This is, so I was expecting that question. Random state is equal to 1 very simply means that if you run the code or I run the code, we start with the same data. So why do we need this? So see, in this step, we are splitting the test data set into 70-30. Okay, 70-30. So if for example, so imagine X and Y have records 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, imagine that is the case. Now, if it is randomly being split into 70/30, in the first random split, these first 7 records go into train, the next 3 records go into test. If next time if you don't mention that, it might take 2 to 8 and move it into train, and 1, 9, and 10 will be in test. If you run the code once again, maybe 3, 4, 5, 7, 8, 9 will move into train, and rest will move into test, and so on and so forth. So what this is doing, random state is equal to 1. It's just saying if you run the code and I run the code, we start from the same starting point, so that the data set that we have for train, test, split, etc. is exactly the same, so that the result that me and you get is exactly the same. So that's the idea of a random state, and from there you're splitting the data. Does that make
Thank you,
sense?
sir.
Okay, so linear model, like I said, just call linear regression, that all that gyan we discussed for 1 hour is done in one step, and it's done over here. Okay, and then once you run the linear regression, like I said, what you want to do is, if I write down this equation over here, you want to build an equation which says mpg is equal to beta naught plus beta 1 into number of cylinders plus beta 2 into displacement plus beta 3 into what do you call weight plus beta 4 into acceleration, right? So with this one line of code, you fit the model, and in this, you pull out the coefficients. So what is it saying? Coefficient for cylinder is minus 0.4, right? So this value for number of cylinders is minus 0.4. Beta 2, which is displacement, is minus 0.003. So this is minus 0.003. For weight, it is minus 0.006. So this is minus 0.006. And beta 4 finally is 0.14. So 0.14. So, and then you have beta naught, which is the coefficient. So the intercept. The intercept is 42.991. Okay, 42.991. So this value is 42.99. So what is this saying? For every unit increase in number of cylinders, miles per gallon goes down by 0.4. For every unit increase in displacement, miles per gallon goes down that much, which is what we saw in our correlation analysis also. As displacement goes up, miles per gallon goes down. As weight goes up, miles per gallon goes down, and so on and so forth, right? So this equation, has kind of is okay. Can it be better? Of course, it can be better, and we don't have time to do that, but we can discuss at a later date how do you make it better and stuff like that. But at least at a first stage, you've run a decent model out here. Okay, and then finally, what you're interested in is to check the R square for the model. So again, simple one line of code, regression model square will give you the R square, and in this case, R square is 0.74. So 0.74, is it good? It's good. Can it be better? Of course, for this kind of a data set, we should be aiming for a R square of 0.85, 0.9, etc., which tells you that. So if R square is low, there's 2 or 3 problems. So, like I said, as a data scientist, you're like a bit of a doctor, right? So when you know something is going wrong, then you have 2 or 3 things you can check with the patient to see, is this going wrong or that going wrong or that going wrong? In this case, just from experience, I can tell you that we need to include more variables. So miles per gallon is not just a function of cylinders, displacement, weight, acceleration. There's probably a 5th variable. Let's say, for example, the make of the car. Let's say, for example, things like the make of the engine and so on and so forth, which can actually influence the mileage. That is not captured in the data. If you capture that in the data, R square can go up. The other reason why R square might be low, because I said there is a correlation between the independent variables, and that might be influencing the accuracy. Okay, so that in a nutshell, is the case that I wanted to cover. Hopefully, you have a decent understanding of what linear regression does, and more than happy to answer any questions or whatever. Does someone have any questions? No?
Sir,
Yeah.
suppose for one model, R is minus 0.7.
R
and
square or R
R
square is
square.
minus
No, R
0.7.
square cannot be minus, sir.
R, okay.
R is suppose minus 0.7. And for one model, it is 0.2. So which one will be better?
So you have to always look at R square rather than R. So in this
So
case,
if you do it square, then 0.7 will definitely be more, no?
Correct. So
Okay.
this answer is more complicated than. So idea is that if we had more time, I will tell you R square is actually not the best metric to look at. There is something called adjusted R square, which takes into account the number of variables that you use in the model. Again, we've run out of time, and if I had more time, I would have gone to adjusted R square.
Okay, sir.
I would, as a data scientist, use MSE rather than R square. But like I said, the business needs one way to interpret it, so you use R square. So, yeah, that that's the simple way of describing.
Thank you, sir. Thank you. Thank you very much.
Yeah. Okay. Any other questions?
Actually, all the faculties, they need the notebook as well as the slides. So
Sure.
after the session, you can share the slides and notebook with me. I will share it with you.
More than happy. Yeah, we'll do that.
Yeah.
All right. So thank you so much. I know we are 2 minutes over time. I'm on LinkedIn. If you have any other questions or whatever, more than happy to connect and answer that. Yeah. Thank you.
Yeah, thank you, Mr. Vijay. Really wonderful session. The examples,
Thank you.
whatever you have given, and okay, the way you explain the linear regression, it was very nice. Thank you.
Thank you so much. Thank you.
Yeah, thank you, everyone.
Thank you.